Let's go to section 5. We will talk about density matrices in quantum information theory. This is a very important concept in quantum information or quantum mechanics. Okay, first, we will see the main fact from quantum physics. In quantum information or quantum mechanics, the most simple quantum state is described by a 2 times 2 complex matrix denoted by here rho. So each component is a complex number. It is a very well-known fact in quantum physics or quantum information. And every quantum state is described by a density matrix. This is, in a sense, from an axiom of quantum mechanics. And actually, experimentalists want to estimate very huge matrix. A typical example of huge density matrix is a quantum computer. In quantum computer, a single qubit is described by a 2 times 2 density matrix, but we have many quantum bits, qubits in a quantum computer. We have to prepare them, and then we want to check the all of qubits. They are ready for quantum computation or not. Okay, and in this talk, we often focus on this very simple 2 times 2 complex matrix called the density matrix. And of course, we can define mathematical definition of density matrix. Definition: a complex matrix is called as a density matrix if it satisfies the following 2 conditions. The first one, trace equal 1. The second one, rho is positive semi-definite. This inequality denotes the positive semi-definiteness. And then it implies mathematically the density matrix rho is always Hermitian. This is a mathematical definition. Okay, now we will show so-called block representation, which is actually 3 real parameterization over 2 times 2 complex matrix. Okay, let x, y, and z 3-dimensional real vector. The norm is bounded by 1. In other words, x squared plus y squared plus z squared is between 0 and 1. They are real. And then we place x, y, and z in each component of the density matrix rho. In this bracket, we set 1 plus z, x minus iy, x plus iy, y minus z, and finally multiplied with a factor half. And here, I denotes the imaginary unit. So we can see it satisfies trace 1 and Hermitian. And if you calculate the determinant of rho, then we obtain this condition. This condition is equivalent to the positive semi-definiteness of the matrix rho. This is a very specific case. In 2-dimensional complex vector space, So we obtain one-to-one correspondence between the space of density matrices and three-dimensional Euclidean space. So the space of density matrices, 2 times 2 density matrices, corresponding to the unit ball in a three-dimensional Euclidean space. If we determine a certain block of vector, three-dimensional real vector, then we can determine a certain density matrix in this parameterization. So this is a Bloch representation. And this three-dimensional real vector with norm bounded by 1 is often called a Bloch vector. Okay, now consider data generating models. We avoid the definition of quantum measurements, so-called POVM or projective measurements. So we avoid complete description of quantum measurements, but we only introduce very specific cases. The following measurements is a mathematical model of measurements, and statistically, this model or way of measurements implies a certain data generating model for a fixed density matrix. Okay, first, we pick up a specific unit vector omega, three-dimensional vector omega, and then this omega specifies a certain physical experiment. Then we repeat n times for the quantum system for this measurement specified by omega. We obtain binary data, and the measurement outcome, denoted by W, is distributed according to binomial distribution. With the success probability, this is a point. The success probability is given by quantum mechanics rule, 1 plus the inner product of omega and theta. Omega is a measurement vector we specify, so we can choose any way. And theta, this is an unknown vector, which specifies unknown quantum system described by the Bloch vector or density matrix. And we can easily see this quantity is between 0 and 1. So this is a data generating model for specific theta and omega. For example, in the last section, we chose 3 kinds of measurements as a unit vector E1, E2, E3. Then we obtain 3 kinds of measurements. Each W is distributed according to binomial distribution. The success probability 1 plus theta j over 2 for each j. So we obtain W1, W2, W3 measurement outcome. We easily estimate the parameters theta1, theta2, theta3. Then, using these estimates, we can reconstruct density matrix. In other words, we can estimate the quantum system from experimental data. Of course, this is a very simple situation. But the rule is very simple. In this two-dimensional complex vector space. Now we go back to the quantum state tomography. The main task in quantum state tomography is to estimate a density matrix from the experimental data. And data generating model or physical measurement follows the law of quantum theory. Of course, we avoid the complete description of quantum measurements, a calculation rule, but anyway, data generating models are given. And data generating models are often binomial or sometimes multinomial distributions. But such distributions are nothing special or nothing new to statisticians. And now we want to apply predictive methods in the last talk to quantum state tomography. The key is the similarity between density matrices and probability vectors. Now let's see the similarity in the next slides. Okay, formal relation between density matrix and probability vector. First of all, in finite dimensional complex space, please recall that we always diagonalize a density matrix with a certain unitary matrix U. Here, the diagonal lines, we can see a lambda 1 to lambda d, they are eigenvalues, real and non-negative, and summing to 1, because of the two conditions of density matrix. You can check easily this. And this property is very important to us because the remark, first one, the dimensional real vector lambda, denoted by lambda, is regarded as a probability vector because non-negative and summing to 1, very formally. And in the above expression of law, U times diagonal matrix times U conjugate. The unitary matrix U represents additional degrees of freedom in quantum domain. Roughly speaking, this is a certain classical or non-quantum part of density matrix. Okay, now let's consider probability distribution over the finite index set from 1 to d. Then probability function p of x, summing to 1 and non-negative, is regarded as a diagonalized density matrix in this form. Just to relocate each component of p of x, p1 to p2, p3, p of d, in the diagonal line. Now, using this formal correspondence, we can introduce two notions. The first one, quantum statistical models. The second one, Bayesian predictive density matrix. Now let's see briefly these notions in the next slides. The first one is quantum statistical model. Quantum statistical model, which is analogous to a non-quantum or classical statistical model, which is given by a parametric family of density matrices. Even if we have a very huge density matrix, many complex components, but we specify such density matrix very few dimensional parameter. And we draw the schematic diagram of a statistical model. So the white panel denotes the whole d-dimensional density matrices. If D is very large, like 100 or 1000, then very huge space, but we often assume a certain parametric model of density matrix. Then, for example, this green surface denotes the quantum statistical model M. And of course, this situation is very similar to a non-quantum classical statistical model in the last talk. In the last talk, we see to predictive method, we consider the whole probability distribution denoted by the white panel is very large, maybe very large. But we often assume a statistical model, which is denoted by green surface. And we focus on this model. The situations are very similar to each other. The second notion is Bayesian predictive density matrix. Bayesian predictive density matrix is formally given by the following formula. So it is the average of density matrix row with respect to the posterior. Of course, we set a prior distribution over the parameter space, then together with the data generating model, we can construct the posterior. We write the formula of the posterior. This P of W given theta is a data generating model, and P of theta is a prior distribution. We have to assume. And now, again, we can see the similarity between Bayesian predictive density matrices, this kind of form, and Bayesian predictive distributions with this form. The average of probability distribution with respect to the posterior. This is seen in the last talk. Okay? Now, in our viewpoint, we can consider quantum state tomography as prediction. In two-dimensional case, using Bloch representation, we can explicitly write Bayesian predictive density matrix in this kind of form. Okay, x, y, and z, the Bloch vector, the summation of x squared, y squared, z squared is bounded by 1. So the prior distribution over this space, and then we calculate the integral for each component. And finally, we obtain x hat, y hat, and z hat. There, actually, the base estimate of the parameter, Bloch parameter, x, y, and z. So, in other words, any base estimate of the parameter is regarded as a component of Bayesian predictive density matrix. Okay, so we neglecting the Bayesian prediction, but we give a base estimate x hat, y hat, and z hat in Bloch representation. Then it corresponds to a certain Bayesian predictive density matrix, rho pi. And if we determine a certain Bayesian predictive density matrix, rho pi, then we can obtain base estimate of each parameter. This is a very important fact to evaluate base estimate in the setting of kernel state tomography. Now, in the next section, we obtain a certain extension of classical Edison's result to kernel state tomography.